Hey guys, today we're going to be talking about the states of matter. Believe it or not, matter is all around us and is crucial to our existence. It is the reason we have our shoes, houses, and bodies. Yet, if everything is made of matter, how come everything appears so unique? I mean, you're telling me that this ice cube and this puddle of water are the same thing? They obviously don't look the same, nor feel the same, nor have the same properties, yet they are somehow made of the same stuff. As we all know, everything in the universe is made up of atoms. The state of matter depends on how these atoms are arranged and interact with one another. And that's what today's video is about, the different states of matter. The main three we will talk about are solids, liquids, and gases. First up are solids. Solids have a fixed shape and volume, and the atoms within solids are packed together. This gives them a more rigid structure. In a solid such as a cube of metal, the atoms are tightly packed and arranged fairly neatly. Next is liquids. Examples of liquids are water, orange juice, apple juice, lemonade, strawberry lemonade, and molten iron. Unlike solids, liquids are usually not arranged as closely. Liquids are generally less dense than their solid counterparts and can move more freely. However, there are cases when liquids are more dense than solids. The biggest example of this is probably water. I'm sure you are aware that ice, the solid form of water, actually floats on top of liquid water. And fun fact, if water never had this unique property, life would not likely exist today. So thanks, water. But do keep in mind that, in general, solids are more dense than liquids. Now, here is a comparison between the configuration of atoms in a solid and the configuration of atoms in a liquid. Notice how the solid atoms are tidier and have a more fixed pattern. On the other hand, the liquid atoms are configured more casually, which allows them to take the shape of their container. The reason liquids look this way is because the atoms have more energy than solids. With the energy, the atoms can move around more freely. This is why solid ice can't move freely, but liquid water can. Alright, gases. Gases, by definition, have more energy than liquids. Oftentimes, gases are much more spread out and are less dense than solids and liquids. Examples of gases include the air we are currently breathing. Like liquids, gases, too, can fill their containers. And here's another comparison. This time we are comparing a liquid with a gas. Notice how the gas can fill its entire container more sparsely while the water is still contained yet packed more densely. So yeah, that's the basics of the states of matter. If you enjoyed the video, make sure to leave a like and subscribe. Anyways, thanks for watching. Psych! There are more states of matter. For those of you perhaps yelling at the screen, Brayden, what about plasma? Yeah, I didn't forget about you guys. So plasma is similar to a gas, but it has much more energy than gases do. In a general sense, these atoms have so much energy that the electrons can break apart from the atoms itself, forming a sort of ionized gas, where the atoms and electrons are separated. This ionized gas has the ability to conduct electricity much better than normal gases. And I'm also willing to bet that you've probably seen plasma at one point or another. Examples of plasma include lightning, the northern lights or the aurora borealis, or even magnetic reconnection, and those videos of people microwaving grapes. The sun is also made up of plasma. In general, most of our universe is made of plasma. According to NASA, plasma makes up roughly 99.9% of the visible universe. This of course includes the sun and other stars, but also the so-called empty parts of space. While there may not be much matter in that empty space, it is filled with a sparser plasma. Alright, anyways, that's the 4 states of matter. Thanks for watching, make sure to like the video, and subscribe if you enjoyed it. Alright guys, see you later. Actually, before I end the video, I just want to tell you something. There's more. Yes, there are more states of matter. All my life, I was like, solid, liquid, gas, plasma. But once I found out, I was like, there's more? That is pretty much the exact reaction I had while researching this video. At like 5 or 6 in the morning when I woke up, I realized that there are sort of other states of matter. Kinds much more exotic than typical matter, though most of these are theoretical in many senses, but so are multiverses. Again, many of these states of matter are theorized. But before I talk about the other states of matter, I just want to go over the phase transitions of matter. I won't really go into detail, and I'm just going to put 2 pictures on the screen of them from Wikipedia. Pause if you'd like, although I hope it's intuitive and sort of self-explanatory. Also, I wanted to mention that the solid, liquid, gas, and plasma states of matter are called classical states of matter. Why? Probably because they are much closer to classical physics than to modern quantum mechanics. Wait, quantum mechanics? Yes, quantum mechanics has to do with many of the non-classical states of matter. So the first other type of matter is also regarded as the fifth type of matter, the Bose-Einstein condensate. And say that 10 times fast. The idea of the Bose-Einstein condensate is that the matter itself stops acting independently and instead turns into a state where the wave function is constant and uniform. In other words, a group of atoms act like a single large atom. Unlike plasma, which is really hot, Bose-Einstein condensates are really cold, near absolute zero or negative 273.15 degrees Celsius. Or, for my fellow American viewers, negative 459.67 degrees Fahrenheit. Okay, that's cold. The Bose-Einstein condensate, or BEC, is created once a gas of what are called bosons, particles with integer spins, are cooled to near absolute zero at low densities. A superfluid is like a BEC, but it contains unique properties. While not all BECs can be superfluids, many can be. And some cool properties of superfluids is that they can climb out of containers, flow through even the smallest cracks of a container, and can flow without friction, as they have no viscosity, and as a result of this zero viscosity, they can also make whirlpools that can last forever. This type of whirlpool has a fancy name called a quantum vortex. Sounds awesome, right? A quantum vortex is also an example of a topological defect. Additionally, superconductors, while not traditionally BECs, share the similarity that they have to be cooled to near zero and have very different properties under super cold temperatures, such as being able to conduct electricity with zero resistance. Superconductors also happen to be incredibly useful and important in the realm of quantum computing. Before we go to the high energy states of matter, let's talk about the fermionic condensate. Unlike BEC, which uses bosons, the fermionic condensate uses fermions. Bosons have integer spins, while fermions have half-integer spins. Fermionic condensates are also made using something called Cooper pairs, which are pairs of fermions that show superfluidity under certain conditions. Fermionic condensates are also harder to produce than BECs due to them using fermions. Okay, now onto the hot topic of high energy states of matter. The first high energy state of matter we have is degenerate matter. Earlier we talked about normal matter, but due to incredibly high pressure, the kind you would find in the middle of neutron stars, matter goes through a sort of transition to become degenerate matter. This type of matter is what neutron stars, white dwarfs, and even black holes are made of. A type of degenerate matter is electron degenerate matter. This type of matter is created when atoms are under such pressure that they sort of melt together. This is common in white dwarfs and the like due to their density. A white dwarf could have the mass of our sun with the size of a city, and the atoms inside are probably fuming under all that pressure. And again, it's that matter that helps keep the neutron stars from collapsing. Another type of degenerate matter is quark matter, or quantum chromodynamic matter, QCD for short. Quarks, as we know them, make up atoms. They're protons and neutrons. Usually these quarks have incredibly strong bonds called gluons. If you try to break them up, they pull back stronger. So quark matter is when the gluons are broken and the quarks are able to move about. This could happen in conditions such as those in neutron stars. Though in usual conditions, quark matter would instantly decay, though the existence of quark matter is still theoretical. And there are also theories about this strange matter, a type of quark matter that might exist in neutron stars. Though there is no real evidence of it existing and its properties are mostly unknown and have yet to be truly proven as of this recording, despite that, from what physicists have gathered, strange matter would contain not just up and down quarks, but a third type of quark that is possibly more stable. Some believe that if the matter is more stable, it can convert our normal matter into strange matter. Again, this is still speculative. QGP, or quark gluon plasma, is when quarks become so hot that the gluons break and the quarks are able to move about freely. And as the name suggests, they're in a sort of soup of gluons. As far as we understand QGP, it flows like a liquid. This is unlike most plasma because normal plasma flows like a gas. This plasma is believed to have existed within the first 0.0000001 seconds of the Big Bang, according to Earth's sky. Understanding this plasma could help us unravel and understand the Big Bang and the infancy of the universe. Also in neutron stars, quarks may form a sort of quark liquid with unknown properties. This quark liquid is currently theoretical and we don't know much about it. Moving away from quark matter, there's also color glass condensate. This matter is believed to exist when nuclei traveling at or near the speed of light collide. When they collide, the gluons become excited and energetic. At these high energies, gluon density becomes so high that it causes something known as gluon saturation. This is where gluons are so packed that they overlap and affect each other. This can lead to the gluons splitting into more and more gluons. In a color glass condensate, the gluons behave like a sort of glass, a barrier, basically frozen in place. I should also mention that this type of matter is also hypothesized, so might not be real. Who knows? Finally, there are the high energy states of matter. This one's pretty cool. It has to do with string theory and what happens to gravity once matter reaches the Planck temperature, or just about 10 to the power of 32 degrees Kelvin. At those temperatures, quantum mechanics and general relativity might be thrown out of the window. So far, no theory can describe what would happen at these temperatures. Thus, this is hypothetical. Nonetheless, this mysterious state of matter is important in the study of cosmology because our universe may have been at this mysterious state at some point during the Big Bang. Finally, but for real this time, let's talk about a time crystal. This is a last-second addition to the video, and I want to include it because it sounds like something from a sci-fi movie. So now, time crystals are a recent phenomenon. They were theorized by Frank Wilczek in 2012. Anyways, Wilczek thought about normal crystals and how their crystalline structures repeated in space. He thought, well, what if crystals could repeat through time? Time crystals are a quantum system of particles that move in a repeating pattern over time while they're in their lowest energy state. So while it might look like the particles are moving, they aren't using any extra energy to maintain motion. Time crystals also break something called time translational symmetry. Now that too sounds crazy, but hear me out. On the screen you should see a circle. Now I'm going to rotate it. Now you probably can't tell that it rotated, but that is because circles have rotational symmetry. Time translational symmetry is symmetry of the fundamental laws of physics and how they don't change over time. So wait, time crystals break the time translational symmetry and thus the fundamental laws of physics? Well, actually, no. Instead, time crystals show a different form of periodic behavior through time rather than breaking the laws of physics. And they still work within our pre-established laws of physics. Nowadays, scientists use the term discrete time crystals to describe systems whose properties can change back and forth over regular time periods. In the case of time crystals, a time crystal's spin could change to be up and down, repeating itself. This could end up being useful in fields such as quantum computers to create quantum computer memory from these time crystals. And who knows what we could do with quantum computers. And well, this video was supposed to be about the states of matter and I just sort of kept rambling on, so sorry about that. But wait, what about dark matter? Well, the thing with dark matter is that we can't really see it or observe it since it doesn't interact with electromagnetic radiation. I mean, it interacts with gravity, but it's a whole nother story for another time. Maybe one day we will be able to talk about dark matter, but I think that is enough for today. For real this time. Thank you for watching.